How's it going? My name is Taebyn. I'm a Forest Park, and welcome to another edition of Math with Taebyn. Today, this is part 2 of Applications of Power series. So I have another video that I used the power of power series to integrate something that you wouldn't normally be able to integrate. And the idea was, and always is, turn what you're having trouble working with into a power series. Find a power series representation and then see what you can do with it. So I'm just going to continue and do 2 more examples of using power series and working with them. And I'm going to assume you know about differentiation, what a power series representation is, and have some experience finding it, and what a geometric series is. Here's my first example. Here's a function, and we want to find the power series representation of it. You might recall the geometric series, recall, don't just might, but recall the geometric series formula. Geometric series is the sum n equals 0 to infinity of x to the n equals 1 over 1 minus x. And of course, that's for the absolute value of x is less than 1. Notice, by the way, this then is the power series representation of the function 1 over 1 minus x. Now here, this looks a lot like geometric series. A common way to approach a problem that you're not sure of where to go, think of, does what you're looking at look kind of like something you can recognize or something that you know? This kind of comes down to the idea of how do you do something you don't know how to do, you turn it into something you do know how to do. This looks like geometric series. It's tempting to just square all of this, that you can't, don't just square all of that. Note, 1 over 1 minus x squared does not, you don't just square this. The algebra doesn't work that way. Squared. You can't do it like that. But recognizing geometric series and that this kind of looks like a geometric series leads you to the idea that, well, maybe I should just try starting with geometric series. Now, so we'll start with geometric series and see what can happen from there. If you look at this, if you are familiar with the differentiation rules, you notice that what we want kind of looks like the derivative of this thing, of what we're given, right? And for purposes of differentiation, I will rewrite this like this. So that leads to the idea of, why don't I try differentiating both sides of my geometric series formula and see what that gives me? A lot of times when problem solving, you've got to just try things. And if you do something wrong, that's fine. A lot of times that'll start pointing you in the right direction. So let's try differentiating both sides here. If I take the derivative of both sides, kind of rewrite this here then, I'm going to try differentiating both sides. And so this was 1 minus x to the negative first power. So I started with the geometric series formula and differentiating both sides. One of the wonderful things of power series is you can interchange the derivative and summation symbol. So that means we look like this. Then the derivative of 1 minus x to the negative 1 power is 1 minus x. Bring down the negative and subtract 1 from the positive. Chain rule says you multiply the whole thing by the negative 1. So this actually turns positive by the chain rule. Easy to miss that. So that's where that negative goes. So I can rewrite this as 1 over 1 minus x squared. Oh, but hey, that's what I'm looking for. So now all I have to do is mess with this side, but I know how to take the derivative of x to the n. So we have that the sum n equals 0 to infinity of n x to the n minus 1 equals 1 over 1 minus x squared. And so there's our power series representation. I wrote it this on the right side instead of the left side of the equal sign. But there you go. Power series representation of this is this. And you can actually start with n equals 1, because when n equals 0, this is a 0. So you might see some books or people actually start with this at 1. It's the same thing. In any case, this is your power series representation. You could pull out an x to the negative 1 and, write it several different ways, but in the end, this is it. Okay, so that's actually lots of fun and exciting. You can use that idea, to just manipulate things around. Remember, the idea is take your given thing and what does it look like? In that case, it looked like a geometric series. So start with that and maybe differentiating, or sometimes integrating everything can turn it into your given problem. So let's turn it around a little bit. The last example was you were given a function and find what series it represents, or what series represents it. Let's go the other way. Given a series, what function does it equal when you add all these things up? Let's use the same strategy, problem-solving strategy as before. Take what you're given and see if you can make it look like something you know. So if you notice, this kind of looks like a derivative, right? Almost, except there's not a negative 1 in the exponent. So if you notice, there's kind of a derivative thing going on in there. Try starting with, that the derivative of x to the n equals nx to the n minus 1, right? And so what we're given, what we want to deal with, is pretty much right there, just the negative 1 thing. But maybe we can deal with that later. Let's just see what we do. Well, if we want a series to show up, we should slap on a summation sign, both sides. Summation thing. N x to the n minus 1. Now, again, one of the fun things with series that you can do is you can switch the derivative and summation symbol. So that means what we have here is the derivative of switch these, the summation and the derivative sign. Okay, now here's geometric series formula. So hopefully if you are good at recognizing things, or you don't have to be good, just the more you work with something, the more you learn to recognize it. This is geometric series. So this is the derivative of 1 over 1 minus x. And then this side, see, I might as well do it now. I can pull out this negative 1. And I end up with, now I really have on this side what I'm looking for. Well, but I know what the derivative of this is. Make sure you can do that derivative, of course. And as I mentioned before, you could actually start this at 1, because the n equals 0 term, that goes away, so you can start with 1. But that's fine. You can start with 0. So what we have, multiply both sides by x to the negative 1 power, multiply by x. I should say either divide by x to the negative 1 or multiply by x. So that's the function that represents this guy. And of course, there's the domain thing. You need the absolute value of x to be less than 1. Yeah, and so that's kind of the idea about these things. Sometimes you might end up integrating instead of differentiating in order to get what you're looking for. So it helps to just keep in mind basic integral and differentiation formulas, because then you can wiggle things in like that. So I hope this has helped you all out. It's a lot of fun and great stuff. And I'll see you next time on Math with Taebyn. Bark, bark.